Okay, so let's start off with our new unit here. So we are going to be learning about gas laws in this new unit. Now, up until now, previous to this unit, we've been talking about the smallest things, talking about atoms, subatomic particles that make up atoms, and then atoms make up matter, and then we went into learning about all the different elements on the periodic table. And then after that, we then moved on into larger scales. So these elements can either become ions and create different molecules or compounds. So we went into different progressively larger increments of scale. Now, gas laws, as the unit title mentions, is going to be dealing about gases, which means we are going to be now talking about compounds or molecules in general, gas molecules and gas particles. So before we start off, there are several important things, or should I say useful information that you all need to know in order to move on forward with this unit. So, first off, useful information that we all need to know. Because of the fact that we have to start relating all these informations and variables into our knowledge and the content that we'll be learning, we first have to go over, well, if we have a specific variable, what units are involved with those so that when we are encountering any calculation problems, we can overcome those and deal with it and be able to identify those. So, starting off, units of pressure. Some of you may be already familiar with some of these units right here. We have kilopascals, torr, atmospheres, and millimeter mercury. Now, these are one of the most common units that you will encounter within chemistry. Now, I'm not saying that these are the only units out there, but these are the ones that you'll encounter the most. So whenever you encounter kilopascals, torrs, atmospheres, or millimeter mercury, you can automatically associate that these values that are associated with these units are about pressure. Now, a quick relationship about some of these values right here. Torr and millimeter mercury actually have the same conversion because, well, millimeter mercury was how they used barometers, and that barometer was actually developed by Torricelli, which is a scientist back in Italy. And that's how that came about, and the units can be used interchangeably. And then atmosphere is one of those that we use in chemistry a lot more commonly as well. Kilopascals you may have heard within weather and whatnot. Now, our next units that we must be able to easily identify are units of temperature. Now, units of temperature, you all are very familiar with the Fahrenheit scale and then Celsius somewhat. Now, we may have already mentioned the unit of Kelvin prior, but I will explain a little bit more in detail right here. So Kelvin is another unit that we are going to be using in gas laws, and most of the values that we deal with specifically about temperatures, when you're given any value such as Celsius or Fahrenheit, they must be converted into Kelvin to make all of these calculations easier. Now, one of the main reasons that we must convert them into Kelvin is because of the very nature and the properties of the temperature scale, which I'll explain in the next slide. All right, so hopefully temperature units are easily identified because there's only technically 3 out there. Well, if we go in more detail, there are 4, but the 4th one you don't really use unless you're going into engineering. All right, so let's talk about our next units that we need to be able to easily identify. We have units of volume. Now, in this case, we are dealing with liters. Also, meters cubed can also count as units of volume because of the fact that anything to the power of 3 we're dealing with are 3-dimensional, and we're talking about volume and space. All right, so these are the 3 main units that you have to be able to easily identify whenever we are encountering most of these gas law problems. Now, we have one more very important set condition that we all have to understand. You're easily going to encounter when you're dealing with gas laws a phrase that's, or let's say abbreviation that is written as STP. All right, now STP, some of you may have already been able to guess, but STP stands for Standard Temperature and Pressure. Now, we're talking about when scientists have unanimously all agreed universally saying that when we conduct an experiment at a specific condition, we want to agree on the temperature and the pressure. And in this case, STP that all of us have universally agreed to is 0 degrees Celsius and 1 atmosphere in pressure. Now that 0 degrees Celsius, if you convert it into Kelvin, is 273 Kelvin. So when we're talking about standard temperature and pressure, you ultimately should be able to associate with saying, oh, if it says standard temperature and pressure, the standard temperature is 273 Kelvin and the standard pressure is 1 atm or 1 atmosphere. All right. If we go into a little bit further, like additional information, there is a standard volume for those who are a little bit more curious, saying, well, if you have standard temperature and pressure, do we have standard volume? Yes, we do have standard volume. However, standard volume only applies if we are in the condition of standard temperature and pressure. And standard volume happens to be 22.4 liters per mole. All right, so if we encounter those types of problems, I will go into more detail in explaining them. All right, so let's go a little bit more and explain about the temperature scale, because Kelvin may not be too familiar for some of you guys right here. So Kelvin versus Celsius. Now, Kelvin scale ultimately comes from what we call the absolute zero temperature. All right, now absolute zero is dealing with the temperature that is the lowest possible, that it is a temperature measured when all particles or all molecules have stopped motion. Because how temperature is measured is because of the average kinetic energy of these molecules colliding with each other, creating heat. And that kinetic energy is converted into thermal energy and creating the temperature that we are able to measure. So, in other words, if particles aren't moving and they are not creating any kinetic energy, that means no thermal energy can be created, which means that there is no temperature, and that is what we call absolute zero. So when we talk about absolute zero, it is a temperature in which all particles have ceased to move, all right? And that temperature is negative 273 Celsius. Okay, so keep that temperature in mind. 0 Kelvin is the lowest temperature possible in the Kelvin scale, and that is negative 273 Celsius. So theoretically speaking, we cannot go below the temperature of negative 273 Celsius. All right, so if we use that as a zeroed out scale, if you look on that diagram down below on the right side that I have put up on this PowerPoint, you can notice that 0 degrees Kelvin on the right side is equivalent to negative 273, which means that the Celsius and the Kelvin scale are only negative or 273 degrees apart, but they're moving 1-to-1 ratio. So in order to find out your Kelvin temperature, is if you have your Celsius temperature, you only need to add 273 degrees to that, and you will get your Kelvin temperature. So for an example, if your body temperature is 37 degrees Celsius, what temperature is it in Kelvin? We can refer to that equation above, saying that the difference is 273. So Kelvin temperature would be 37 degrees Celsius plus 273, giving us 310, which is 310 Kelvin. All right? Hopefully that made sense. Now, our very first gas law, Boyle's law. Now, Boyle's law is a law that was first discovered by Robert Boyle, who was an English physicist slash chemist slash philosophist and etc. He discovered this through a series of experiments and was able to prove that at a constant temperature, if the volume of the gas increased, that the pressure will decrease. Or if the volume of the gas decreased, the pressure increased. Now, from this relationship, if one goes up, one increases and the other decreases. You notice that it's a relationship kind of like a seesaw. When one side goes up, the other side goes down. And we call this relationship an inversely proportional relationship. So the pressure and the volume, which are the variables involved in this law, are inversely proportional at constant temperature. So if I were to summarize it, it is saying that if we have constant temperature, when pressure goes up, volume will go the opposite direction and decrease. And the other way, if pressure goes down, the volume will increase. Now this creates a very simple equation, which is our first equation, which is P1V1 equals P2V2. Now, P obviously is the symbol for the variable pressure, and V is the symbol variable for volume. So when we're talking about P1V1 equals P2V2, the ones indicate first pressure and V1, first volume, is equivalent or the same as P2, or the second pressure, and V2, second volume. Now this actually is able to generate a very simple equation, graph. It's an inversely proportional equation, which means that the graph will actually end up looking like this. Notice that the V, which is the x-axis, and the pressure, which is the y-axis. When you have a low volume, you tend to have a high pressure. And if you have a high volume, you will have a low pressure. This is exactly what the inverse proportionality means. Now, when you look at a graph, it's kind of hard to grasp, but if I were to show you this simple diagram here, think about a volume that you have and a lid or something like a piston that holds it in spot. If you're not putting any pressure to that volume is not changing. But if you were to press down on that piston, the volume inside that piston will decrease, but that's because you have increased the outside pressure. So do you notice that inverse proportionality right here? You can easily notice it from this easy example. Now, another prime example that you have at least hopefully experienced is either if you've been driving up in the mountains in Colorado or if you've been in a flight, an airplane. When you're flying on an airplane, either takeoff or landing, or if you're driving up in the Rockies in the Colorado mountains. Now, if you were to have a bag of crisps, or a bag of chips, as you would say, and you're driving up the mountain or the airplane is taking off. When somebody gets higher and higher in altitude, people describe that pressure is dropping, which means pressure is decreasing. Now, as you're going higher and up, some of you who have been able to observe this, what happens to that bag of crisps or bag of chips? It gets larger and larger. It looks like it's starting to inflate. This is a prime example of Boyle's law that you have been able to hopefully experience live. All right? As you go higher up, as the pressure decreases, it inflates, the volume increases. And then when you're landing or when you're driving down the mountains again, the pressure starts increasing again, and then the volume starts decreasing, and your bag of crisp chips goes back to the normal size. All right, so these are the prime examples and the relationship that Boyle's law has. So overall, to summarize, Boyle's law, importantly, deals with constant temperature, and at constant temperature, the variables are pressure and volume, and we talk about those having an inversely proportionate relationship. Think of it like a seesaw. When one variable goes up, the other variable goes down. So hopefully you guys had this helped understanding what Boyle's law is about.